3D printers today are faster and make prettier prints than ever, but what about print strength? That, I think, is still a weak spot. Watching my P2S with the thermal camera, I saw something that could help to change that. So today we are testing whether the simplest possible extrusion path can actually make stronger parts than the standard way. Then after testing, we are going to scale it up to real-world size prints as well. So today we're going to answer the question, is the absolute simplest type of extrusion possible also the strongest extrusion? So stick around to find out. A few weeks ago, I was testing some small pins for fidget toys because they kept on breaking on me, and while I was tweaking the designs, I noticed something. Adhesion actually improved when the layers below exactly matched. So if we're looking for strong parts, there's usually two typical ways that we would do that. One is just to add more walls, and that's great in an area that is identical. So if you have an area like this column that comes straight up, all of those walls will line up exactly, and that should give us pretty strong parts. But if you look at the transition between those two areas, if this is the base and this is the column, normally you're going to see one wall and then an infill type that comes in and it goes directly below that column. So then we have an area below that column right at the transition point, one of the weakest areas, and it doesn't line up, and that is going to make for a weak spot. Now there is a different way to do that. This is typically done based off of looks. You can have one outer wall on your top layers. So instead of doing it that way, you can actually change it back and have it as the standard to match the amount of walls that you have, and you will get layers that line up better at the transition point. So that should make stronger parts. That is one option. And another option would be to keep a few outer walls, but then to set your infill to 100%. And then what you get in that scenario is the same type of thing, your one outer wall, but you get alternating layers. So you'll see a layer directly below going the opposing direction, and then in the column, every other layer opposes each other. So because these layers do not line up exactly, there's not going to be a lot of contact between them, and it's going to make for a weaker final product. So there are some ways that we can get stronger parts just by adjusting the current settings that we have available to us. But I'd also like to address one other thing, and that is with the current method of extrusion, if you're going to use walls like this, it's not printing into hot plastic. What it's doing is laying extrusion around, allowing a little bit of time every time it goes around for that plastic to cool. And I really don't think that's helping us at all. Instead, I think it would be better to find a way to extrude into hot plastic every time if we can. So to set up for our test, what I'm going to be doing in Bambu Slicer, this can also work in Orca Slicer, is I'm going to bring in my part. So I'm going to paste in the part, I'm going to right click and say add modifier. In this case, the modifier is the same part, but it is a hollowed version of that part. And there are a few ways to do that. I'll show you in just a minute how to do that. So they basically are identical. I'm going to flip this up as well because I want it to print vertically. And then to get these to line up, we can say center, center that part, center this part. They line up exactly now. So to get the change to work properly, we need to go over to the global tab under strength, and we can set the walls to 0. We can set the infill density to whatever we want. I think I was using crosshatch. 15% is fine. And now the important part is where it says detect narrow internal solid infill under the strength tab, we have to uncheck that one. And now we can go over to the objects tab and we can start looking at the modifier. So the modifier is only going to apply, of course, where it is actually intersecting that part. So there are some areas in here where the original part or the original properties will take over for the infill, for example. So the modifier for the walls is right now set to 0. That's good. And now for this to actually work out properly, we need to change the top shell thickness to be at least the height of the part or higher. So 300 millimeters. And the reason for that is because we're using the top shell thickness to get identical layers. It doesn't really work any other way, at least not that I've found. The layers will typically alternate back and forth, so they would crisscross, and we instead want every single layer to be identical. So then we can go down to internal solid pattern, and I'm going to change it to align rectilinear. And we can change the infill to 0 for this one. And now you can see that if we go down, every single layer, with the exception of the infill, is lining up all the way right down to the bottom. And that's exactly what I was looking for. So there's just a few little steps, a few little tweaks to make this work for you if you wanted to try it for yourself. Now, another version that we want to set up is one with a single wall around it so that we get the looks, but we also maybe get the strength of this version as well. At least I think we're going to get to the strength. So to do that one, all we need to do is go back to the modifier and add one single wall loop, and then slice that one as well. And then we have the same thing except for one wall going all the way around. That's on the inside and on the outside as well. Now, if you're trying to do this for something that you do not have the file for, because I created this, I was able to create the hollowed version really easily. You can bring in an STL file into Mesh Mixer, and this is a drone body. You can go to Edit, and then over to Hollow, and then you specify how hollow you want this part to be. So right now we have 2 millimeters for how hollow it is. I'm going to maybe change it to 1 millimeter or so. And then the density up. And I'm going to say update hollow. And you can see there, it has updated it. So we have all of these internal hollow sections. And then all I would do is export this file and bring it in just the same way I did the last one and overlay the two by centering them exactly. To explain why I think this might work, I've drawn up two samples. We have the proposed method and then the standard method. The standard method has 6 walls and the proposed has the equivalent of 6 walls, but we have that solid internal infill. It's actually top layers, and then every single layer lines up, of course, like we showed. So in that proposed method, we have the start point either here or we have the start point here, and it's going to come around. It's going to lay filament or extrude filament into itself. So it's putting filament into a hot piece that's already been extruded. It's going to come around the center infill and then connect back to itself. So for the most part, it is always extruding into itself with the exception of that very last bit of extrusion. And the benefit of that is it is going to have better bonding to itself, but it should also retain heat in a much more isolated area while it's extruding into that area as well. So it's going to be hot beside, but it's also going to be hot below as well as that heated filament is extruded in that area. So that's completely different than the standard approach. In that method, we're extruding walls, but we're allowing time in between for every single bit of extrusion to cool. And it's also covering a lot more area as well. So as it goes around, every time it's going around, cooling is occurring, and it's going to lay beside a cooled area. Now these parts are quite small, so it's not going to impact these ones as much as if you had a really, really big part. That's probably where this proposed method would be more beneficial. So there's still time for the entire part to cool, but we are extruding in an area that's going to retain some of that heat, and there should be benefits from that. So here's the test that I had in mind. We're going to print 3 versions of the same part. One is going to be the usual way with multiple walls, slow perimeters, faster infill, and then 2 more parts using my new proposed method. For our testing, I like the fulcrum style or lever style stress testing because it does do a good job of mimicking the real world breakages that we would see. And the parts that we're testing today are very simple. They have a base and a column that comes up and an area that I can hook onto for our load testing. So here is our test setup. I have a slow motion camera pointed directly at the parts so we can see exactly what's happening. And then here are the parts. I have PLA and I have PETG carbon fiber. These ones here are just aligned. There's no wall on this. These are aligned but with one outside wall. And then these would be the typical way that you would print, although they do have a lot of walls and a lot of tops and bottoms, and that's across the board, or the equivalent to, I should say. So I'm going to get these mounted onto our jig and get these in. For the testing, I'm going to remove all the weight for our crane scale, make sure we're on newtons, and then set over top and down. I also thought it was a good idea to print just basic PETG versions because this has less cooling on it and they tend to have much better layer adhesion. So I ended up testing 30 different samples in total, and only one really came in a little bit lower than the rest of them. Everything else was pretty consistent in results. So in the blue here, we have the fully aligned versions. So that's the ideal proposed method, although it may not look so good. And then in the red, we have the single walled version. Again, everything is aligned underneath that. And then in the yellow, we have the standard method, yellow or orange, or maybe that's peach. So if we take a look at the results here for PLA, in the blue, exceptional results, and for PETG carbon fiber, again, very good results here. But if we jump down to PETG, that is not the case. In fact, it actually went the opposite direction a little bit. For a little bit more clear picture, if we take a look at the averages for the PLA test pieces, 149.3 compared to the standard 102.2 is a 46.1% improvement in strength. So that's pretty big. If we take a look at the PLA version with a single wall, 124.4 compared to 102.2, that's a 21.7% improvement in strength. So still pretty good. If we take a look at PETG carbon fiber, again, very good results here compared to the standard. Again, 46%. This one's 46% bang on. But if we look at PETG carbon fiber with the single wall and the aligned layers compared to the standard, it's actually a weakening of minus 1.9%. So not an improvement in that particular case. Now, if we take a look at PETG Basic, it actually goes the other way. Not by a lot, but it's worth noting. So we have the aligned version compared to the standard, it's a minus 6%. So it's a weakening by 6%. And then if we have the one wall versus the standard, it's a minus 17%. So it's a weakening by 17%. So where we have materials that have either a lot of cooling and poor layer adhesion, maybe because of cooling, or just in general they have poor layer adhesion, it seemed like we got a pretty big bonus from the aligned versus the standard method. It's not as big of a benefit if we have a single wall around there and then the aligned version. But then if we have something that already has really good layer adhesion and we're trying to make an improvement upon that, it actually went the opposite direction by a little bit. So not an improvement in that area, but still very interesting results. And it seems like they are very consistent with the exception of the just one you can see down here of 88.3, whereas the other results came in at 127 and 128. So that one might be off by a little bit. So if you're wondering to yourself, what does this actually look like made into a real 3D print? Is it even possible to make into a 3D print? The answer to that question is yes, actually it is. And it turned out better than what I was expecting. Now I did make a little bit of a change, and I made sure that the infill layers were all aligned the way the bridging had to be to make it work out because of this print. This is actually a fairly complicated print. There's lots of overhangs, and it was set at a pretty severe angle as well. So definitely does not look as good on the bottom as it does on the top side. The top actually looks really nice. So this might actually work better for some prints than other prints, but I wanted to throw kind of a difficult print at it to see how it would turn out. Now I have this one here, but I also printed the standard version because this is PETG carbon fiber. It doesn't typically have great layer adhesion, so it's actually a really good application for this. I also didn't think printing this in PLA would be a good idea because it has the motor mounts on here. Those could get warm on a PLA print and it could deform those areas. So PETG or ABS or something like that would probably be better, maybe even nylon for this application. Let's take a look at what this looks like as it's normally printed. So I printed this on the H2C and I printed the other one on the H2C. And you can see some areas it still struggled a little bit there, but overall it doesn't look too bad. Definitely cleaner on the bottom than the one that I printed with the infill version. So what I'm going to do at the end of this video, I'm going to have a video of each of these so you can compare them for yourself, but really there's no way that I can actually compete because I'm missing certain line types, and those line types have different properties for cooling, for example, or for speed. All I have is infill properties, and you can see on the bottom especially that it didn't turn out quite so nice. It is still a pretty decent looking 3D print, at least on the top, and this was a difficult print. Also, the material that I chose was PETG carbon fiber, and it is pretty difficult to print when it comes to overhangs and bridging as well. So it is possible to print in this way, but it's not possible to get the same kind of finished results, at least on those outer shells, without adding that extra wall on the outside or walls. But at least it did turn out, and it actually looks pretty neat. So if you have ideas for strength improvements to 3D prints that might look better than the one that I've come up with, please let me know in the comments down there below, and it might make it into a future testing video. I want to say thanks to each of my patrons for supporting this channel and making videos like this one possible. And if you're in the market for a 3D printer and you want to know which ones I would recommend, I have a very short list in the video description down there below. Thanks for watching, take care, and I hope to see you on the next one.